All right, so we're looking at the next Gauss's law super example today, which is to use Gauss's law to find the electric field due to an infinite line of charge. And if we're looking at our objectives, which we should be, we're still on the same one that's that we looked at yesterday, right? Applying the law along with the symmetry arguments determine the electric field for a planar, spherical, or cylindrically symmetric charge distribution. Yesterday we looked at a planar charge distribution, and today is a cylindrically symmetric charge distribution, or a charged wire is maybe an easier way to think about that. All right, so we're still on this objective A.3.D.2. All right, so the goal for today is we want to find the electric field due to an infinite line of positive charge with a uniform linear charge density lambda. That's the Greek letter lambda. So what we're saying is that we have positive charge spread out like this over an infinitely long wire, and lambda tells us how many coulombs per, how much charge there is per unit length. So can we, before we get started, can we figure out or say what the unit is for this quantity lambda here, which is the linear charge density, or the charge per unit length?
Wouldn't it be just coulombs per meter?
Exactly, coulombs per meter. Perfect. Right, how many coulombs of charge is there for every meter of this infinitely long wire? Right, and again, in reality, we don't have too many infinitely long wires, but the results we get work pretty well for finite length wires, as long as you don't get too near the ends. And this is a pretty useful example because in electricity we have, in electricity and magnetism, wires come up a fair amount of the time. So it's good to know the electric field. All right. So we're going to use Gauss's law to find this, right? Remember, Gauss's law says that the total electric flux, which we know we can get from doing the surface integral of the electric field dotted with the infinitesimal area vector, is just equal to the charge that's inside our Gaussian surface divided by the constant epsilon naught. All right. So what we have to do is we have to figure out a good Gaussian surface to draw so that we have enough symmetry that this integral becomes much simpler and possible to do. All right. So the Gaussian surface I'm going to draw for this one, just like yesterday, is a cylinder again, but it's going to be oriented a little bit differently. All right, so I'm going to draw a cylinder around the wire. So here's what the cylinder is going to, so something like this. All right, so I've got a cylinder around the wire here, and I'm going to say the cylinder is a radius r, so that's going to be something we can change. And we'll figure out, maybe we can make a prediction about whether or not the electric field is going to depend on this radius r, right? We know that with a point charge, it definitely does, right? The farther away we get from a point charge, the weaker the electric field gets, right? It goes to like 1 over r squared. We saw for an infinite plane of charge that it doesn't, right? That it didn't matter how far away we got from the infinite plane of charge, the electric field was uniform, it was the same. So does anybody want to make a prediction? What do we think? Is the infinite line of charge, is the electric field going to depend on how far away we are from that? Is it going to depend on r?
Sorry, I was writing the question.
I'm asking if we are going to, if the electric field that we solve for using Gauss's law, is it going to depend on how far away we are from this wire? Is it going to be more like a point charge where, yeah, the electric field gets weaker when we get farther away from the wire? Or is it going to be more like the plane charge that we saw yesterday where the electric field is uniform and it didn't matter how far away we got from the plane?
I'll say it's uniform.
Say uniform, all right. And I got a couple responses in the chat saying that it is going to be weaker. So let's see, right? I mean, that's something we got to figure out. So we'll be curious to see in our answer if this R shows up or if it cancels out somewhere and it doesn't show up. All right. So why don't we get started here? Remember, if we want to make sure. I want to bring back up just for a moment the conditions that we have in order to make sure that we can use Gauss's law, right? And those were in the textbook here. So remember, we want to make sure that for each of the, every part of our Gaussian surface, at least one of these conditions has to be met, right? Either the value of the electric field can be constant over that portion of the surface, which means we can take the electric field out of the integral, make the integral much easier. We can express that dot product E dot dA as just E dA because E and dA are parallel to each other, and that makes the integral much easier. Or the dot product is 0 because E and dA are perpendicular, in which case there's no flux through that part of the surface. Or, of course, if the electric field is 0 over some part of the surface, that's going to give us no flux as well, too. All right, so let's see. Let's look at each of these parts of our Gaussian surface and see if we can simplify anything. So first we need to figure out, we don't know yet if the electric field is going to get stronger or weaker as we get farther, or uniform or weaker as we get farther away from the cylinder. We'll find that out. But we can make a good prediction about what direction the electric field is going to be. So for example, if I have a point P or any point, say over here, right above the wire there, what direction is the electric field going to have to point if I'm right about here?
Upwards?
Yeah, it has to be upwards, right? It's got to be away from this wire, right? We know that, positive charges are going to force other positive charges away from the positive, away, repel. And the electric field tells us the direction that a positive test charge would feel the force. And in this case, it's got to be upwards, right? It can't be, you might think, well, maybe it's off, off a little bit diagonally one way or the other, but that can't be right because it's an infinitely long wire, right? There's the same amount of charge to the right as to the left, no matter what point we pick. So any charge to the right is going to, any force to the left from the charges over here is going to cancel out by the forces to the right from the charges over here. So we can argue from symmetry that right here the direction has to be, straight up, right, away from the wire. What about down here? At that point, what direction would
down?
Straight down, right? The electric field here has to be straight down, right? Directly away from the wire. Right, and if we kind of look end on, let me draw a quick end on view of the wire, right? So here's our infinitely long wire, it's coming out of the page into the page here. We can tell that the electric field is always going to point directly away, right? Radially outwards.
So is this like the opposite of the other superexample?
It's not I wouldn't say it's the opposite, because in the other superexample, we also argued that the electric field has to point directly away from the plane of charge, right? So it's kind of similar in that sense.
Yeah. But I meant like the way it affects the cylinder. So like this time we'd have a flux on the edges.
Yeah, exactly. So what? Yeah. So
on the side, sorry.
You're right. So when we look at the cylinder, right, and that's where we're going next. Now that we kind of understand, or that we've argued, I hope we understand that the field has to be radially outwards, right? So up here, it's we can go all along the wire and draw the field. It's a little hard 3D, but if I pick a point right here, above the paper, right, the electric field's going to be pointing out of the page. Right? And if I pick a point a little bit below the paper, the electric field will be pointing into the page. But yeah, so now we can figure out what is the flux through each of these surfaces, and I think Mahmoud's already kind of figured it out. Like, what's the Is it going to be 0 through any of them? Which, let me label these. We've got this end cap, we'll call surface 1. The other end cap we'll call surface 2. And the curved cylindrical part we'll call surface 3. Which of these, if any, can we say right away it's going to be 0 flux? And I got in the chat Ali saying that the caps are going to be 0. Anybody disagree with that? I would agree that the flux through the end cap, so through surface 1 and through surface 2, are both going to be 0. Right? And that's because the area vector for surface 1 points this way, perpendicular to the electric field, and the area cap, or the area vector on surface 2 points to the right, also perpendicular to the electric field. Right? So we know the dot product of E dot dA over the entirety of both of those caps is going to be 0. So the flux through both of those is going to be 0. Okay with that part of it? So now let's try to figure out the flux through the curved portion, right? The curved cylinder portion of the surface. What do we know about the direction of the electric field and the direction of the normal to the area? And remember, the normal to the area for this cylinder, right? Parallel, right? The area vector for the cylinder is always pointing just directly outwards from the cylinder, right? Just like the electric field is. So those two vectors are in the same direction, E dot dA, right? So that means this becomes, since E dot dA, they're in the same direction, is just going to be the magnitude E times magnitude of dA. So that satisfied the second condition there in the textbook. Yeah. That satisfied the second condition there in the textbook, that the electric field and the area vectors are parallel, so that we can reduce the vector equation to a scalar equation. The other thing we can do, it also satisfies condition 1. We can say that the electric field, it doesn't matter where on this surface we look at the electric field, we can say that the magnitude of it is going to be the same, right? Because everywhere on this surface is the same distance away from the wire. So if the wire changes, even if we see that the electric field varies with distance, that still doesn't, we're still going to have a constant electric field over just this surface, right? Every point on this cylinder part is the same distance from the wire. So we can argue that every point on the cylindrical surface is going to have the same magnitude of the electric field. Questions about that, or any disagreements with that? So what I'm saying there is that the cylindrical surface satisfied both conditions 1 and 2, right? The value of the electric field can be argued by symmetry to be constant over the portion of the surface, right? Because every point on that is the same distance from the wire. And number 2, right? We already said that the dot product E and dA are parallel. So that means that we can take the electric field out of the integral because we know it's going to be constant over that. So we really just have the integral of the surface integral of dA. And that's just right. If we integrate if we just integrate over the infinitesimal area, then we're just going to get the total area, right? If we integrate over dA, we're just going to get the area. So all we need to know is what is the surface area of the cylinder here. Does anybody remember that from geometry or can kind of figure it out?
Is it pi r times h something?
Oh, two pi.
2 pi r.
I'm sorry.
Yeah.
8.
So I heard a couple things. I heard, is there going to be an r squared or is it going to be r? And
R squared.
it's r squared?
Pi r squared times height.
The way you say it like that does not make me confident.
Squared times height. Well, that's true. We should let me label, let's not call it height because we're kind of, I'm drawing it horizontal here. Let's call it, let's just call this is L. So is so at the pi r squared times length is going to would give us the volume of the cylinder, right? Because that's the area of the end cap times this length. That's the volume of the cylinder. But that's not what we want. We want the surface area, right? So how we can do that? If you think about maybe cutting the cylinder along here and unrolling it, and then you've got a rectangle.
2 pi r times L.
Yeah, there you go. So it's 2 pi r times L, right? If we unroll the cylinder, and let me see if I can try to draw an unrolled cylinder. Yeah, maybe. So that we can kind of flatten it out, right? This is still L, and if we unroll it, this side of it, I guess this is partially unrolled, this side of it is the circumference of the end cap, right? Not the area, so 2 pi r. Right, so when we fully unroll it, we have a rectangle that's length by, length on one side and 2 pi r on the other side. So the area is just 2 pi r times L. Oh yeah, 2 pi r times L, right. Okay with that piece of it? So that means our flux here, well, our total flux, right, is just going to be the electric field E times the surface area of this cylinder, which is 2 pi r times L. So that's our total flux through the surface. Any disagreements there or any confusion so far? So we're almost there now, right? Because Gauss's law tells us that this value has to just be equal to the amount of charge that's inside divided by epsilon naught, right? So we know that E times 2 pi r times L is equal to the charge inside over epsilon naught. And we have to be a little bit careful here because we can't just solve this for E and leave that as our answer, because L is something that we kind of made up, right? We could make this cylinder any length we want, and the electric field, you can think about it. The electric field at any point on the cylinder shouldn't matter how long our imaginary cylinder is. The radius is a different story, right? Because if we make the radius bigger, then we're farther away from the wire, so we might get a different value there. And we also don't know necessarily how much charge, or we don't know yet how much charge is enclosed in the cylinder. But we can figure that out pretty quickly, right? Because we know the linear charge density lambda. That's given to us. So the next question I'm asking here is how much charge is inside the cylinder? What's the charge inside going to be equal to in terms of things we've already written down? How much charge is inside this cylinder of length L? Take a look at lambda again, right? What's this? This is the linear charge density, right? This tells us how much charge there is per meter. So how can I relate the charge density, so the charge per meter, with the length of this cylinder to figure out the charge inside? Oh, I can barely hear you.
Oh no, I'm thinking out loud. Sorry.
No problem.
Um. Hmm. Well, can't you just take the equation you have on the left and just make it equal to Q, to just the charge encased?
Yeah, well, this is the charge encased, right? Q inside. Oh, so you're saying solve this, but the problem with that, why I don't want to do that is because this L, right?
Mhm.
We would expect not to have the L in our final answer.
Okay. So, wouldn't you just divide by L on both sides to like cancel it out, or you don't? Oh, you don't want the L in general. Okay.
Well, I can try that, and that will probably get us there, but we should be able to figure out what the enclosed charge is. Let me get you a little closer. We know how much charge there is per meter of this wire, and we also have a length of our cylinder.
Oh, just E times L, or am I blanking out still?
You're right, not E times L. It is L times something.
Or is it? Oh. My.
So the charge inside here is the charge per meter times the number of meters that this cylinder is.
Okay, that makes more sense. Yeah.
And if we look at the units, right, the lambda has units of coulombs per meter. The length of the cylinder has units of meters. If we multiply
Coulombs per meter squared.
coulombs per meter squared, the meters cancel out, and we have coulombs, right? And that's the charge, right? Charge is going to be in coulombs.
Okay.
So if something about this part's not clear, ask a question. But what I'm saying is that now that we can express the charge inside our cylinder as the linear charge density times the length of the cylinder, if we plug that back into our equation, right, E times 2 pi r times L equals lambda times L over epsilon naught. Now we have an L on each side, right? So it cancels out. And the only things we have left are the electric field and then things that are given to us, right? The linear charge density. This R, the distance so it does turn out, well, let's solve it for E and see what it is. It looks like we have lambda over 2 pi r epsilon naught. Right, for the magnitude of our electric field. So what that means is since the R is still in the equation, right, and it's in the denominator there, it doesn't matter what we make the radius of our Gaussian cylinder. If we want to find the electric field farther away, we have a bigger R and we have a smaller electric field. And that does make sense if you think about it, because with a point charge, right, a point charge, when you get farther away from the point charge, the electric field gets weaker by 1 over r squared, right? So it gets weaker quickly. For this long line charge, it doesn't fall off quite as fast, right? Instead of an r squared in the denominator, we just have an r. So as you get farther away, the electric field does get weaker, but it doesn't get weaker as quickly as from a point charge. And that's kind of because as you get farther away from the wire, the farther ends of the wire kind of come into view a little bit better. Is maybe a qualitative way to think about it. And then with the plane of charge that we saw yesterday, right, that didn't depend on the distance away from the plane at all. And that's kind of because if you think about it, the farther away you get from an infinite plane, it still looks like an infinite plane, right? Much more of the plane kind of comes into your view as you get farther away from it. So it's kind of somewhere in between, right? It doesn't get weaker as quickly as a point charge, this infinitely charged line, but it does get weaker as you get farther away. Questions about the second Gauss's law superexample. All right, so the next one we'll look at, the third superexample, is basically a spherically symmetric charge distribution, so a solid ball of charge, and we'll take a look at that one next week.